Today we want to look at another lesson in Unit 3. This is going to be working with rational expressions. And this will be coming from chapter 14 in the book. So in 14.1, we're going to start with simplifying rational expressions. Again, rational kind of means we have this numerator and denominator. So in other words, we have division present. Also, we would call these fractions. So if we look at these first examples, simplify or reduce the following fractions, write the answers with positive exponents only. So remember, when it comes to numbers like 12/15, we're just looking for a common factor. Again, if you're not really good, you can always use your calculator and do a prime factorization of this. You know, you could kind of put the 12 over here and the 15 over here as scratch. And, you know, remember the prime numbers are that 2, 3, 5, 7, 11, sometimes 13. So again, you know, we always start with 2, and we do know that 2 does go into 12 6 times, or again, on your calculator, you can just divide 12 by 2. If you get a whole number, it's good to go. And since 6 is also even, we know that 2 does go into 6, 3 times. But 2 won't go into 3, but the next prime number is 3. And 3 does go to 3 one time. So for 15, 2 doesn't go into 15, but we kind of see that 3 does go into 15 5 times, and 5 does go to 15 one time. So remember, we can actually break this down into a prime factorization. If there's that word factoring again, changing it back to a product of numbers. So 2 times 2 times 3 would be the numerator, and 3 times 5 would be the denominator. And notice how there is a common factor of a 3 and a 2 that we can divide out. And therefore, we're left with then 2 times 2 on top, which is 4/5. So again, this step could also be done mentally, if you will. So for 24/36, can you think of the greatest common divisor between a 24 and a 36? If not, you can always do a prime factorization off to the side. 2 goes into 24 12 times. 2 does go to 12 6 times. 2 does go to 6 3 times. And 3 does go to 3 one time. 2 does go to 36 18 times. 2 does go into 18 9 times. 3 goes into 9 3 times. And 3 goes into 3 one time. So if we break it down into a factorization, we have 2 times 2 times 2 times 3 in the numerator, and 2 times 2 times 3 times 3 in the denominator. And we notice that we do have these like factors. Remember, when you divide the numerator divided by the denominator, 2 divided by 2 actually turns into a 1. And since we're multiplying by 1s, we don't show it. So the other pair of 2's divides out. And then we have a 3 divides out. So it leaves me with a 2 in the numerator and a 3 in the denominator, so that's 2/3. So actually, the greatest common divisor would have been actually a 12. 12 would have went into the numerator and denominator and gave us this 2/3. So if we look at this next example, notice how, if we will, we want to try to get away from doing all this with prime factorization since the numbers are small. Notice how, if we look at the numbers 2/4, notice how I can divide a 2 out of both of those. And that's going to give me a 1 over a 2. If we look at the x's, 2 minus 1 is going to be 1x, and that's going to be left in the top. So we have an x on the top and a 2 on the bottom at this point. On the y's, there's 1 y on the top and there's 2 on the bottom, so I can cancel out one pair of y's, and I'm left with a y on the bottom. There's 3 z's on the top and 1 z on the bottom, so again I can remove 1 z and I'm left with 2 on the top. So remember, wherever there are more of the variable, that's where it's going to be in the fraction. So I think we said 2 there though, not 3. So 3 on the top, 1 on the bottom, that would leave us with 2 on the top. So the 9 and the 3, notice how the the 9 and the 3 do have a common factor of 3 that I can divide out. Leaves me a 3 in the numerator. So again, if I start my fraction bar, the 3 is on the top. There's 2 A's on the top, 1 A on the bottom. So again, I can divide out 1 A. That leaves me 1 A on the top. There's 3 B's on the top and 1 B on the top, bottom. So I can kind of cancel out or remove a B. And that leaves me 2 B's on top. And then there's just a 1 on the bottom. Since there's a division of 1 there, we don't keep the 1 in the problem. We just write this as 3A B squared as a simplified version of that. So we've kind of done that already in our previous lessons in chapter 11. Now, what we're going to get into is some of the stuff that we just did in chapter 13 with some of these factored forms of polynomials. So notice that the numerator and denominator are in factored form. And notice how in factored form, if we can see like factors, we can cancel this out. So if you look at A, notice how the x plus 2's are the same on the top and bottom. So we're allowed to remove those. So that x is on the top, and then x plus 3 is the factor that's remaining on the bottom. And that would be described as simplified. If you look at B, notice how the 3 and the 6 have a like factor of 3 in them. So that turns into a 1, that turns into a 2. Notice how the AB's will actually just totally divide out. The A plus 4 and the A plus 3 are not like factors, so they have to remain. So the only thing really left in the numerator is the A plus 4. The only thing left in the denominator is that 2 times this quantity A plus 3. So we can leave it like that, or if we want, we can also multiply the bottom out into expanded form, which would be like 2A plus 6. So you could also express it in that form. Either one is acceptable for the most part. Again, in my lab, you just have to look more closely to see if they really care. I prefer to leave it in fractured form myself. I usually like to just leave it in this form. It saves me a step because there's not much to gain to expand it out necessarily. So if we look at C, notice how there's not a 2 in common in the top and bottom. If you look at the x's, I'm going to go ahead and make my C here, make a fraction bar. If you notice on the x's, there are 2 x's on the top and 3 x's on the bottom. That means there's going to be a canceling out, or there's going to be 1 x left on the bottom. So 2 remained on the top. So the 2 stayed on the top. The x's, I have an x left on the bottom. Notice that 2x minus 1 and x minus 1 are not like factors. So that binomial 2x minus 1 will stay in the numerator. So I use parentheses to show multiplication, that factored form. And that x minus 1 stays in the bottom. We would leave it like that. Again, you could multiply it all out if required, but if it's not required, I would just leave it in factored form. In D, notice how there's an x plus 3, there's an x minus 3, there's an x minus 4, there's an x plus 4. None of those are factored. So those, they're all factored, but there's no like factors, if you will. So that would stay as is. So D would be considered reduced. It's already considered simplified. But the only thing you can do is expand it out, the numerator and denominator. So what we want to do is we want to reduce these rational expressions. And the way we're going to do that is we're going to use factored form. So if we look at the numerator, the x plus y, so I'm going to just write the problem for x plus y over 4x squared plus 4xy. So if we look at this problem, the x plus y is not factorable. If we look at the denominator, notice how they do have a common factor of 4. They also have an x in common. So I am allowed to pull out a 4 and an x. In doing so, that's going to leave me so if I pull out the 4 and the x, that's going to leave me 1x and a y. So that's going to leave me x plus y. So notice how the numerator and denominator both have an x plus y in them. So since those are like factors, we're allowed to cancel those out. So remember, when you divide that out, that leaves me a 1 in the numerator and a 4x in the denominator. So, we'd have a 1 over 4x as our simplified version of that. So if I look at b, I have a squared plus b squared over a squared minus b squared. Notice that the numerator is not factorable. So the bottom is factorable, but I don't think we're going to gain anything by doing that. So a squared plus b squared is, since that's not a difference of squares, and there's not a GCF, and also how the denominator is a difference of squares, I could factor that into a minus b times a plus b. But there's nothing to gain. So really, we would consider this already reduced. It would be considered simplified as is. So simplified or reduced, there's nothing to gain in that problem there. If I look at C, I have x squared minus 6x plus 9 over x squared minus 9. So again, if you look at the top, notice how the x is a perfect square. This 9 is a perfect square. That would be a 3. So if I make some little notes here, this is a perfect square. This 9 is a perfect square. The catch is, if you multiply the 3 times the x and double it, does it give you the middle term? Notice how that does give you 6x. So that kind of means that this was a negative, since there's a minus sign in the middle there. So that means this is going to be actually a binomial square. In other words, it's going to be that perfect square binomial. So the numerator is going to go ahead and factor into x minus 3 squared. The denominator, notice how that is a difference of squares. That's going to be x minus 3 times x plus 3. So notice how there's 2 x minus 3's on the top and there's 1 x minus 3 on the bottom. So I can cancel out one of those x minus 3's. That leaves me an x minus 3 in the numerator. And there's going to be an x plus 3 in the denominator. And that would be considered simplified, since those are not like binomials. Those are not like factors. So looking at D, I have 3x squared. I'll bring that down here. Don't have much room over there. So if I have 3x squared minus 12 on the top, and if I have 6x plus 12 on the bottom, notice on the top, we do have a common factor of 3 that I can pull out. So if I factor a 3 out, in other words, divide the 3 out, that's going to leave me an x squared minus then a 4. Notice how the x squared minus 4 is also a difference of squares, so that factors a little bit further. So 3 times then x minus 2 times x plus 2 would be the factored form of the top. On the bottom, the 6x and the 12 have a common factor of 6 in them. So I pull the 6 out, or in other words, I divide it out. That's going to leave me an x, and 12 divided by 6 would actually be a 2. So that would be the factored form of the denominator. So if we look at this, I have 6 times x plus 2 there. So if we simplify this, notice that the 3 and the 6 are like factors. I can divide out a 3 and leave a 2 on the bottom. And the x plus 2's will divide out. So as far as the remaining factors, we see an x minus 2's left in the numerator and a 2 is left in the denominator. And that would be considered simplified. So E, we have a minus b over b minus a. Notice we like to have things in the same order. So if I have a minus b on the top, it would be a good idea to write the bottom the same way. That would be negative a plus b. Now notice how these look kind of close together, but they're not quite because of the signs. But notice how if there's a negative leading coefficient there, we can actually factor the negative out on the bottom. So this a minus b would be fine on the top. I can factor a negative 1 out or a negative out. And when I do that, what's going to happen is in the parentheses, the signs are going to change. So that negative a is going to turn into a positive a, and that positive b is going to turn into a minus b. So notice now, though, how we do have like factors. There is an a minus b on the top and bottom. So remember, when that all divides out, that turns into 1s. So the answer is going to actually be a negative 1. So that would be the simplified version of e would be -1. So in reducing rational expressions, we use what's called factoring.